Okay. Ladies and gentlemen, we are going to continue our makeup course in this Thursday. Thursday evening, 6:30 to 9. Okay. And we're going to stay in the same room. Is that right? Yes. Okay. This Thursday evening, 6:30 to 9, we're going to have another makeup course. Okay. If you can make it, make it. Okay. All right. So let's continue to our. Your way you are doing your tutoring job? Yeah. Are you get paid? 12. Okay, 12. Yeah, please come over here. All right, continue our discussion about the optimal and the greedy search. Well, I just let you know, whatever you hear from your senior students or your friends, I just tell you one thing: whatever they say, they might not be best for you. I'm not saying they are wrong. I'm saying whatever they suggest might not be suitable for you. Okay, you are the only one who understand your whole situation, and the best move right now might not be the best move of your entire career. A lot of success stories, for example, don't ever trade one thing, okay? Don't ever trade the wealth with your health. That's a bottom line I give to you, okay? That basically, or in plain English, that's don't ever use your liver or your legs or your arms or your any organ to trade for your money. It's not worth it, because you don't have a backup liver, you don't have a backup kidney. Okay, that's the bottom line. That's the most precious thing that's given by God. Okay, don't ever trade that with money. It's not worth it. Okay, I have seen too many sad stories. I have a friend who is 4 years younger than me. He was the general manager of Giga, the big one, right? And he died at 47. 47, under 50, because of a heart attack, a stroke. And his wife and his kids are in America, and he worked alone in Taiwan to earn big money. I still remember he owned like 4 million shares of Giga's stocks. Okay, it's cost $1 billion, but he died. So his wife and kids are going to enjoy whatever he left behind, but not him. Okay, he died at 47. A lot of sad story like this, and I had a college a friends reunion last Friday. Okay, I was the only one still working in a school. Okay, and most of my friends, college students, already retired. They had a lot of money. Okay, some of them are general managers. Some of them are board members of big company like Realtek, or Novatech. But the thing is, they barely walked. Well, it's a trade. I still can play basketball every Sunday with a lot of guys. I still swim. I still dive. But the only thing that most of my friends can do is just sitting there watching television and reading newspapers. That's all. And they have a lot of chronic disease, like the diabetes problem, okay, metabolism problem. Well, it depends on what you think, okay? I don't have the same amount of money that they earn. Okay, it's impossible. Okay, most of them have thousands of stocks, or millions of stock of shares. It's a lot of money. I just let you know, it depends on what you are looking at. I know that a lot of people will say that money is not everything, but money is the best thing to solve most of their problems. The answer is yes. I agree with that. But the bottom line is, okay, after you solve most of the problem that you think, and the price you pay is your health. Is that worth it? Think about that. Think about that, all right, before you make your move. All right, okay, let's go back to our left edge algorithm. This is a greedy algorithm, greedy solution. It will not give you the best solution. No way. Okay, but it gives you a solution which is called a suboptimal, or at least it's acceptable. So basically, we formulate the channel routing problem this way, okay? With basic routing algorithm, assume one horizontal segment per net. We switch the pins from left to right. You might ask, why not right to left? Well, it's symmetric, okay? It's basically the same idea, okay? No matter you were left to right or right to left, it's still a greedy algorithm, okay? So we assign horizontal segment to lowest available track, okay, like this way. So we started from the leftmost pin that we want to do the routing. Then we assign the track for this net and do the connection. And then we move our pointer to the right to hit the next second group of signal we want to do the routing. We give it a M1 goes to the top, and the second net, the second metal for this net, then goes to the destination. That's it. Okay, and keep doing that. Eventually, you will get one solution for your routing. Is the best? No. Okay, but it's doable. Okay, this is a search way. So let's go to the example, a full example for you. It's called a left edge algorithm. Oops, sorry, what happened? Weird. Hold on a second. All right, okay. Now let's see this problem. Okay, if you're given the channel routing like this, what are you supposed to do? Okay, A have to go to A, B have to go another two B's on the top, and then C. Okay, so this is how we do it. Okay, we do it step by step to let you know what the left edge algorithm is about. Okay, we search from the left to right. The first pin we run into is A. So we do the routing for A. Then the second pin we will run into is B. So this is the net for the B. All right, then the tricky part is C. The tricky part is C. Okay, you will see that, oh, okay, we run into C. So why don't we just go over here and then go to the C over here? Is that all right? Yes, it is all right. It is one of the solutions. But the best thing for the left algorithm is that this algorithm will check whether the used check can be reused or not. See? So if we go over here, then go to the top of this C, how many horizontal checks we're going to use? 3. Is that right? 1, 2, 3. Instead of generating a new check, the left edge algorithm asks you to search whether the previous check can be reused or not. So instead of using this one, the left edge algorithm will go over to check. Jesus, we have a lot of room over here. So why don't we just reuse it? If we do the routing for C this way, instead of using 3 checks, we are going to use just 2. Okay, that is called the left edge. So the left algorithm asks you to assign the lowest number of check to be the new one, to check this one first. So every new net, okay, will check from the bottom to the top to see whether the previous checks can or cannot be reused. So the C will check over here. Oh, Jesus, we have a space over here that will save you a lot of cost. So why don't we just use this one? So that is the idea. See that? So the total number of checks horizontally is only 2 instead of 3. All right? So this is the left edge algorithm. Excuse me. Okay, but there is a limitation for this kind of algorithm. It is called the nets are tangled each other. Okay, they are tangled each other. For example, this one, see? If we follow the left edge algorithm, the first one we found is B. So we'll do B routing like this way, all right? So you can do that easily, okay, because the problem happened when we have a pair of nets. They are sitting on top of each other. So if we do the routing for the A first, this way, with M1 and M2, then M1. So what are you supposed to do for the routing of B? Okay, if you use the M1 over here, right, and then M2 over here, then M1, can I use it? Because there is a short circuit. They cross each other. It's there. If you go over to the top, okay, we have a short circuit over here. It's not doable. Or either way cannot be done. Okay, the only solution, there are two solutions for this part. Solution number one is get out of the room, okay? We have to get out over there and come back to find B. That's ugly. Why is ugly? Because you don't know what's going to happen outside of this box. Okay, there might be animals over there. There might be tigers or lions sitting in the middle. Then your poor little, rabbit could be running into trouble. All right, because the jungle's outside. So there's a bad idea. All right, bad idea. So get out of the safe zone, comfort zone is a bad idea. Another strategy that adopted by most of the people is used this way. It's called a dog leg solution. They have to use this kind of stair shape to get out of the problem. So the B can be routed this way. All right? So this is a dog leg wires. And the dog leg will give you a lot of trouble because it needs 3 horizontal tracks instead of 2. So it is a trade-off between the feasibility and the cost. Okay, this is the second solution. Use a dog leg. Use a dog leg. So now you understand. You find out one thing. Okay, how the hell we can predict or we can foresee whether we need a dog leg problem if we are given a net routing problem. There is one algorithm for that, which is not addressed in the textbook. Most of the textbook. It was addressed in other literature. It is called the vertical constraint graph. So this is a graph for you to understand whether you have a problem of the dog leg or not. I don't think I have that one in my PowerPoint. Yeah, it is called the vertical constraint graph. Okay, I'm going to show you the example. This is a very useful method to judge whether a dog leg was needed or not. The basic rule is that use a directed graph to denote if A is vertically above B. If there is a loop, a dog leg wire is needed. So, okay, let me use a plain English to tell you what is that. So let's assume, okay, this is a channel. We have a lot of cells on the top, many cells in the bottom. Right now we are given, for example, pin number 1 and 2, 3, 4, 5, for example, whatever that is. And the nets to be connected is like something like 5, 4, 5, 2, 3, 1, 4, whatever random number is, okay? So you check whether, okay, they are sitting on each other, on top of each other. So we check. If they are aligned in a grid, same grid, we got to be very careful about that. Oh, this is deliberate design. So they are, perfectly lined up. So we want to know whether we need a dog leg or not. So we draw the figure, okay? So the vertical constraint graph is that when number 1 is sitting on the top of of 5, so we draw this figure. 1 on the top of 5, okay? Then we got to change. Do some change over here. They are not supposed to line up. 1, 2, 3. Okay, for example, this way. Then 2 is on the top of 1. So 2 is on top of 1. See that? All right? Then 3 is on top of 2. 3 is on top of 2. Okay? Then 4 on top of 3. But unfortunately, we are going to have a loop because 5 had to sitting on the top. When we see a loop like this, it is guaranteed you need a dog leg. Otherwise, you cannot do the routing. It is called a vertical constraint graph. Okay? When you do this kind of a graph drawing, and you see that all the arrowheads, okay, unfortunately, they form a circle, a loop, then definitely some dog leg is needed. Is that understood? All right? It's very easy. So this is just a very simple example. You can do a little bit more complicated example. All right? Understood? So this is a loop. Whenever we find a loop, a dog leg is definitely needed, okay, to solve this problem. Dog leg means to break the loop. It's called the vertical constraint graph. It is meant to judge whether a dog leg is needed. Okay, now let's go to a more complicated example. This is called the rat's nest. Okay, it's just like, how a rat is running in the house. Okay, so this, before you go to a larger scale of routing, okay, this figure is going to tell you where is a traffic jam. Okay, where is the traffic? The more wires in the small area, that means it's a jam area. In this figure, you see that where they are here. Because a lot of straight lines cross this area. That means you got to move, okay, do the swap of certain cells so that the density of these wires can be equalized everywhere. Otherwise, you're going to have a very hard routing problem in this jam area. Okay? This is called the rat nest. This can be generated by certain software, okay? But in your design, okay, I don't think you need it, okay? This is used to judge the placement before final routing. So let me rephrase again. Before you do the routing, you got to make sure the placement is good. Otherwise, you're going to have a lot of trouble to do the routing, okay, after you do the placement. Okay, then after you solve all the routing problems, now the next thing is that the wire. How big the wire, how wide that is. A lot of students, they don't give a damn when they do their layout. That is why some of my students' chip, some of the students' chip do not work after the chip is back. But they always say, my simulation was good. Okay, even my post-layout simulation was perfect. How come my circuit does not work after the chip was fabricated? Well, the thing is, you never consider the current problem. Current. You got to have enough current, not just voltage, you got to have enough current. Because the current just like water in your house. You have water or no water, that's one thing. But the important thing is that, do we have enough water in the house? Okay, for example, every day, how much water you need? Okay, according to what the doctor says, you need 4 big cups. Okay, like over 1,500 cc's per day. Okay, we call that the sufficient number, sufficient amount of water. Okay, but you say that, okay, I drink a small piece of water, a small glass of water, okay, 100 cc. Do you drink? Yes, I use the water. But is it enough? No, that's not. Okay, if you keep drinking water like that, sooner or later you're going to have a kidney problem because you do not give enough water to your body so that you can drain all the poison out of your body. Then your kidney will be hurt very soon. So take my advice. Don't drink those bubble tea. Don't drink the bubble tea. Okay, bubble tea is not healthy. I'll give you some numbers, okay? Please do not spread the word on. Okay, how many calorie you need for a single day? Calorie. How many you need every day? Okay, I'm an old man. I'm 60. Okay, according to my demand every day, I need like a 15 calorie to 20. That's all. Okay, and you are young. Maybe you need a little bit more. I think it's 20. I think it's about 20 to 25. That's enough. That's enough. But do you know how much a usual size of a bubble tea with a lot of delicious bubbles and a lot of sugars? Okay, just single cup it's almost 1,000. Okay, 2 cups, that means more than enough every day. And it's kind of sad when I see a lot of students, have a glass of a bubble tea every day. Okay, I'll call that as a suicide. Okay, it's a suicide every day. Okay, if you are not talented in the IT design, that's fine. Okay, but every day, please touch your own belly. Okay, when you're sitting on a chair like that, and you see that the fat drop out of your belt, then you gotta be aware that you have some kind of a healthy problem. I don't mean you, young man. But that's just a message for you to understand. You are so young. You are not supposed to have big fat drop out of your belt. Okay, that's sad, and it's not healthy. Okay, you are going to pay the price for that. It's not about how attractive you are or how pretty you are. It's about your health, right? And do you know what is the body fat percentage that a person should be? I'm not talking about BMI. Okay, BMI, doctor will tell you a number. Okay, give it a guess. What is a BMI for myself? I'm below 24. Okay, my body fat is about 20. Okay, it's an amazing number for age 60. Okay, a lot of professors see that. They barely walked, not even run. Okay, I participated in a marathon 2 weeks ago, a half marathon. So think about that way. You got to enjoy the money you earn. Okay, you don't want the doctors to enjoy your money, right? When you are old, you all have parents, right? So think about this. How frequently your parents go to the hospital? In the last 5 years, okay, the only reason I go to the hospital is for the physical exam, that's all. Even a cold or something, I never see a doctor. Okay, in the past 3 years, I was not affected by the COVID-19. Even if I was infected, I feel nothing. Don't give a damn, okay? Think about that, okay? So let's go back to the current. You gotta have enough amount of current to drive your chip, otherwise it won't work, trust me. So the width of your metal lines is very important. So wire length is determined by layout architect, but we can choose a wire length to minimize the delay. not only the functionality, even the amount of current is enough. Okay, we like to make it faster, so we need larger amount of current to drive the chip. So wire weights can be varied with distance from the driver to adjust the resistance, which drives the downstream capacitance. What does this mean? Okay, let's go to the plain English. I'll show you some example. The best way to do the wire sizing is that you have to use a bigger wire, okay, bigger wire, wider wire, okay, close to the power supply, basically. And the size becomes smaller and smaller when it reaches the terminal of your blocks or your circuits. So this way is called the tapering. Okay, this is the best way to do that. This is close to the power supply. And then the power supply means to give you enough amount of current for everybody, every block in your chip. Then becomes smaller, smaller, and to the end. Just like the water plant, a water supply system in a city. Okay, we use a big tube from the water factories or water resource. Then use a smaller pipes in your house. So it's become big, medium size, and smaller. This is how the water supply is done in the city, and this is what is a current supposed to be done in on a chip. All right, it's called the tapering. Okay, it's getting smaller and smaller, and a lot of students forgot to do that. Is that you got to give enough current for everybody. So, for example, right now you have an adder over here, you have a multiplier over here. Okay, you have to calculate how much they need. Okay, because all the currents of the adder or the multiplier, they come from the same source. Okay, you cannot use a single poor, narrow wires to give them the current. Let me tell you one thing, that the wire is not ideal. Okay, on silicon, it has resistance, it has limitation of width, so you got to give them enough width so that they can supply enough current to drive everybody. So basically, the idea is that the width over here must be equalized to the summation of the width here and here, so that everybody has their own current to do their job. All right? So different branches of tree can be set at different lengths to optimize the delay. That's why. Okay, this is tapering of wiring trees. All right? And this is called a spanning tree. And a lot of students use this way. This is bad. This is bad. Why? Because as you see here, the width over here, and sink 1 and sink 2, okay, is wider than the width from the source. So that means the source cannot give enough amount of current for these two sinkers. And then, let's assume they work. They will be very slow. They'll be very slow. So this is a bad idea. It's called a spanning tree. And students like it because it's simple. But I'm telling you that it will create a problem. It will give you trouble. Right? It'll give you trouble. That's why a lot of students, my graduate students, they always crying or complaining that the chip doesn't work, and then they challenge that whether TSMC or UMC are lousy foundries or not. But well, let me put it this way. I trust them more than the students. Called the spanning tree. And this is another bad idea. See that? Again, right now you can do the judgment right here. See the width over the width of sink 2 and the width of sink 1. The summation of the width of these two branches are big. It's bigger than the width of the source. And it's called a standard point. Okay? And this is a bad idea as well. Standard tree. Is it workable? Yes. Logically correct? Yes. But when it comes to the speed problem or the delay problem, or even worse is that the functionality problem. Sometimes it will not work. Okay, now it's going to be very messy right now because students hate mathematics. Okay, but unfortunately we have to go to this part. It's kind of messy, but don't worry, I will give you the simplest way to do the analysis. All right. So this is called the tree. It's an equivalent circuit of two branches. All right. So we have a source over here, right? And we have two branches, and each branch has its own load. But since we use the metal as a wires, so these are equivalent circuits. We have parasitic resistance and capacitors everywhere. The longer the wires, okay, will give you the more resistance and the more capacitances. And this is called the RC tree. And we like to estimate what the RC could be, what the delay could be, based on the very simple analysis. And in this case, okay, we are going to use another talk to tell you how to do that. It's called the effort approach. Effort approach. Okay, it's a very simple way to do analysis. It's not as accurate as a SPICE, but it will save you a lot of trouble when you do the design. Okay, so we are going to introduce the effort approach, but right now, let's go to something else. It's called the RC transmission lines. So right now you understand all the wires, okay, they are made of metals, and metal is not perfect, okay, they always have parasitic resistance and a capacitance, all right? So students like to use a very simple, straightforward design. Okay, let me draw some figure for you, so for you to understand. Okay, so right now let's assume we have two signals. They want to transmit. They are asked to do the transmission from A to B. So right now you draw a piece of single metal, and this is a transmission line. Okay, the length is, for example, it's L. Okay, length is L. Right? Now, according to the EM wave theory, very, very simple, it's called a transmission line theory. The delay from A to B is proportional to the R square. It's not R, it's R square. If you don't believe me, go back to check your EM textbook. Okay, so it's L squared. The longer the while, okay, the worse the delay. Okay, it's not linear. It's a second power. Okay, the order of 2. So you want to have a faster speed. Faster way to do that is that we cut the entire wire into 2 segments. Okay, then we have a buffer in the middle. So here become Q to the L. Q to the L. So the new delay plan will be proportional to right? So we have a very nice answer that we like. It will become this way. So we simply cut into half. Okay, according to the transmission theory, we can reduce the overall delay by half. Is that right? Okay, but don't forget this. We have a helping hand, and this guy is going to create some delay as well. This is delay by buffer. So you have to add this one. It's delay by buffer. So what if the delay generated by the buffer is less than half of the original delay, then we have some advantage. Is that right? So this is the usual thing we do. Okay, we cut into half. Okay, we use something in the middle. I always call this booster. Okay, it's going to use a booster. And this is something that you already did. Okay, it is created by inverter and inverter, even number of inverter. So the signal comes over here to be boosted again, then go to the second half of the travel. Okay, definitely it will help you to do the to reduce the delay, overall delay. So that is what it says over here. See, RC transmission line. R0 is the driver's resistance, C0 is the driver's input capacitance. Okay, if you follow this way, we can divide the entire piece of transmission line into K segments. And every segment has a single a unit length, something like that. And in between every segment, we need a buffer. So we can keep dividing into half, all the way down. But the thing is, there is a bottom line for that. If you keep dividing the segments into small pieces, then we need to add more buffers. Sooner or later, the delay generated by all the buffers will be larger than the reduction that you gain from the division of these wires. So very interesting. There's an optimal answer for that. Very interesting. Okay. So the H equal to 1. That's a single single buffer. Single buffer. You are going to get this number. Okay. R0 is the driver on this side. Okay. It depends on how big your transistor to drive that metal wire. And R int and C int means the single piece of parasitic resistance and capacitances, right? So we have optimal number for this one. K equal to this equation and H equal to this one. Somebody already solved it. So you cannot go unlimited all the way down to the small pieces of metal wires. It's impossible. There is an there's an optimal solution for that. The answer is over there. You can go to Google search to find out this answer. It's already addressed. I just let you know this way can help you to do the to help you to reduce the delay. Right now, the students like to use the ChatGPT, right? ChatGPT, okay, can you search that? The ChatGPT has already have this solution for that. Can ask if you ask that thing correctly, you can get to know that. But this funny thing will give us a lot of trouble in the future. Our ChatGPT, and students use that to do the homework and come up with a composition. But the thing is, according to my observation, I use that as well to test. Okay, I ask ChatGPT, what is the performance of Professor Chao-Ching Wang in the last 30 years? And well, the ChatGPT gave me that, my expertise is optical electronics, but God is my witness, I never do any optical electronics. Okay, they gave me some crazy idea. They gave me that, they showed me that something I've never done before. What kind of lousy things is? But the thing is, that kind of machine, the more people use it and give it a feedbacks, means that you are going to help that machine to train. Basically, they give it for free, means that they let all the people around the globe to help the company to train that machine. All right? Okay? Now they have a ChatGPT 4.0. Okay, right now they start to charge users for that. $20? Well, $40, I cannot remember. You gotta become their members to use that. All right, And this is an example to follow this method. Okay, we call this a buffer insertion. If you use a minimal size inverter to drive a metal wire, and it's very big, 20,000 times 3 lambda, and the driver size, this is a very typical MOS transistor, okay, 3.9K. We are going to see this number very soon. And the parasitic capacitance. And these are the characteristic R and C of the metal wire. Then you're going to see that. This is a number you get. Plug in, okay? That's all you got. So if you want to do that, according to this equation, you're going to need about 100 buffers to get the optimal speed. Okay, and another thing about the layout is that the crosstalk. Crosstalk is that students hate most because it will give you a lot of trouble when you want to do the measurement. Okay, we have the first one, metal wires, and we have another one here, and they are very close. They have these are 2 metal wires, and they are close to each other. Just like when I talk over here, the next room will hear what I say. Okay, it's called the crosstalk. It's an interference. Okay, and nobody likes it. All the signals that we don't hear is noise. So crosstalk slow down the signals. So it takes a long time to settle down, so that increase the settling time. So 2 nets in analysis, the one giving us a trouble is called the aggressor. Okay, the one who create a problem, it causes interference. Okay, and the other guy who like to stay still, stay quiet, is called the victim. Okay, this is a killer, this is a victim. This is aggressor, this is a victim. Okay, so how are we to do the analysis for this part? Okay, 2 pieces of metal wires, they are sitting close to each other. This is the equivalent circuit model. So the aggressor, because we have 2 conductors, they have a gap in between. So basically, we can use the capacitor to do the modeling for this kind of behavior. So this is a driver, and this is a metal wire on the top. It's an aggressor net. And this is another guy who likes to sitting there doing nothing, enjoy their day, but somehow he hears somebody talking over the wall, okay, over the channel, okay? And unfortunately, their directions of current or voltage are not the same, okay? Because this guy wants to go down. It's a falling edge, but the aggressor said the signal is going up, okay? They are in totally different directions than what happened over here, okay? Because the original signal wants to go down. And then suddenly, the guy sitting next to my room send me a message, goes up. Then I have to force a bump, then comes back. And that is ugly, because that will take me a long time to settle. So that is a delay. Okay? What even worse is that, okay, it never goes down and then bumps back and stay on the top. That's the worst case. Okay? That'll give you a totally wrong answer, wrong expectation. So this is aggressors and the victims. So how are we going to do the analysis for this part? Crosstalk. Crosstalk because of a capacitor. Okay, this capacitor might not be real. It could be a parasitic one. So capacitor does not like to change its voltage instantaneously. So a wire has a high capacitance to its neighbors. When the neighbors switch from 1 to 0 or 0 to 1, the wire tends to switch as well. And this is called a capacitive coupling or crosstalk. Okay, this is a official definition. The crosstalk, the consequence of crosstalk is that the noise, okay, the noise on that vector, okay, because I like to go down, and right now I'm forced to go up. That's bad. And that increases the delay. And sometimes even worse is that it creates a wrong answer. That's really bad. So this is crosstalk. So how are we to do the analysis? Okay, now this is a two piece of metal wires, and let's rotate 90 degrees, goes straight into the board. So what are the parasitic capacitors? Adjacent capacitance, that's where created in between, and their capacitance to the ground over here. All right. Okay, so let's assume the layers above and below on average are quiet. So the second terminal capacitor can be ignored. Okay, that we don't care about this part because it's kind of small, but the adjacent here is really big because of big current. And effective adjacent capacitance depends on behavior of the neighbors. This is called the Miller effect. Okay, Miller effect. So let's assume that A is a guy who's jumping up and down. And there are three possibilities for the B wire. The first scenario is that the B wire is a steady voltage, okay? It's a constant, okay? Nothing will be changed. And the second scenario of B is that it is switching the same as A. Okay, when it goes up, my signal also goes up as well. The worst case is that the switching of B is different from A. That's the worst. Okay, so this is constant. This is do the same switching as A. This is opposite to A. So what is going to happen in those, and the box is over there. For the scenario one, B is a constant. So the effective capacitance is the ground plus the adjacent. And MCF stands for the mutual, okay, capacitive factor is 1. Because, okay, I'm steady, I don't care, right? And if the B is switching simultaneously with A, that there is no voltage difference, okay? And the only thing effect is the ground, that this is 1. And there is no mutual capacitive factor, okay? Because we are the same. Okay, you goes up, I goes up. You go down, I go down, all right? The worst case is this one. A goes up, B goes down. So the delta V right now is 2 VDD. Okay, you goes up, I go down, and the difference between us is 2 VDD. And then the effective capacitance is 2 times of adjacent. And the mutual capacitive factor is 2. Okay, this is the worst case. This is the worst case. Don't worry, okay? So let's do some simulation to find out what's going to happen in the time domain. But before that, we can do some mathematical analysis. We consider those signals, those effects created by aggressor is modeled by this way. Okay, this is aggressor that we consider the worst case. And there is an adjacent capacitance. And the signal will be passed over here to affect this one. Okay, this is guy's, well, it's really bad. And is a victim. I just sitting in my house and doing nothing. Suddenly somebody, okay, knocked on the wall and give me a lot of noises. Okay, and this is ground. So the delta V on the victim wire is modeled this way. C adjacent over this 2, okay? And times the delta voltage created by the aggressor. And this can be easily modeled by the simplest circuit theory. So check this out. Usually, this one is bigger than this one. Okay, if this is big, this is small, then the overall number will be very close to the delta V from the aggressor. Okay, right now let's assume they are the same. Let's assume they are the same. So if they are identical, there's a 1/2. So at least half of the the voltage drop on the aggressor will be passed to the victim. But still very bad. That might affect the functional correctness of the victim. So let's go to see some interesting analysis for this part. Okay? So victim is driven by a gate that fights the noise. Noise depends on relative resistance. Okay? So the victim driver is in linear region. This is very bad. Okay? Aggressor in the situation, this is the strongest. So let's assume victim is weak, aggressor is strong. So what's going to happen over here? This is the same model. And the only difference between this equation and the previous one is this factor. Okay, 1/1 plus k. Okay, and k equal to what? Two delay factors, tau of aggressor, tau of victim, and tau of the aggressor equal to the equivalent resistance of aggressor plus 2 capacitive over here. And this is the victim, on victim side. So this is just modeling, all right? So you can find all these equations over anywhere. But this one is going to show you some interesting results. Based on these assumptions, so what's going to happen? You don't like it, okay? Now this is a simulation based on the equivalent model. So this is time. Now right now, let's assume that at a certain time, the aggressor jumps from 0 to VDD. Okay, well, that's assumes 1. And we assume that C adjacent are equal to the C victim. So right now, let's see what happened over here. If the victim is not driven by anybody, okay, it's just a simple straight wire, no one cares about it, okay, no one loves it, what happened? Then, this is the worst case. The outcome, the voltage of the victim will be half of the aggressor. Okay? And if the victim is driven by certain devices, for example, half of the driver, equal size of the driver, okay, or double size of the driver. So that means this is a small, the medium size, and this is a big size. Okay? So the bigger the victim, okay, the bigger the victim, the less effect that it will receive. So every wire, okay, must be driven to prevent possible crosstalk. If the size is too small, then, for example, this one is only half the size of the driver, and the signal on that victim will be pulled up, then comes back. And take a long time to settle down. All right? Okay? So remember that all the wires must be driven carefully, so that we can prevent any bad things happen. Excuse me. So this is the time domain simulation to tell you the fact. All right? And this is another issue. Okay, when the victim is attacked by two aggressors, that's even worse. The victim is attacked by two aggressors. And these aggressors, they might not, okay, switch in the same direction. Okay, it's very complicated. All right, and of course, some researchers already did research for this part. Okay, and when this is how to model in this problem, and this is particularly important for those students who work in the RF domain, because it happens a lot. It happens a lot. Because RF circuits is less complicated. I'm not saying less complicated. I should say less devices are used. Basically, the RF circuits need amplifiers, MOS, and then inductor and capacitor load or something like that. It's not as complex as digital circuits. But the thing is, they are very sensitive. They're very sensitive. And from time to time, these kind of things happen. So some researchers already spend a lot of efforts to find out what could happen, okay? The victim net is surrounded by two aggressors. So these are the modeling. They have to know what is the thickness of these wires and what is the spacing between the victim and the aggressor, and how big the width is, and what is the distance between the victim wires and the substrate ground. All right, and the most successful researchers in this part is a Japanese. This is a professor in Tokyo, University of Tokyo. It's called Sakurui. Yes, Sakurui. And this is what he reported about 10 years ago, okay? But this is just directly copied from his thesis. So basically, if you increase the spacing, that means the distance between the victim and the aggressor, that will help, okay? And there are two ways to do that. It's relatively RC delay. If you only have a smaller delay, you got separate these two wires as far as possible, and then increase the size of the driver. Increase the size of the driver. Okay, that's just tell you two directions, that's all. Okay, we don't have to go to the mathematical part, it's very complicated. All right, crosstalk delay. Well, this is a short summary. There is an optimal wire width for any given wire spacing at the bottom of the U curves. Optimal width increases as spacing between the wires increases. That's the two conclusions given by Professor Sakurai. Okay, and if you're interested, you can go to search his paper. Well, this is the end of talk number 6. Now we go to number 7, and hopefully that we can finish the chapter 7 in this coming Thursday. We still have like 15 minutes. Let me introduce you what the lecture 7 is about. Well, the IC design is about two things. The first one is power. The second one is a delay. Delay is AKA is also the speed. So we have to analyze the circuit before you do the design. So in this lecture, we're going to discuss IOC and the delay model. Basically, L will be taken away from this course because all the students only focus on digital design, low speed. Below 300 megahertz, we don't consider it's RF frequency. So RLC, virtually speaking, is only about the R and C. Inductor is rarely considered in this course. Okay, in fact, it never happened before. But when your research, if your research in the future is going to do the high frequency design, okay, RF circuits, you need to understand the inductive effect. But that's another story. So basically, we have to introduce you how to do the estimation of resistance and capacitance. Inductors, there are rules, but it's not that accurate. Not at least not accurate as the R and the C. Okay? Then we talk about a delay model. And then another factor we have to consider is the power. As I said at the beginning of this course, power will be everything in the future. Without power, we don't do nothing. Okay? Power, how to analyze the power. And the last one is PVT variations, which I ask you to do the homework. Okay? So let's talk about the resistance, and let's see how far we can get to in the next 10 minutes. All right. So all the materials on the silicon, you can consider it's a slab. Okay, it's a slab. And it's uniform. It's uniform. Let's assume the process is perfect. Given by the TSMC, we trust their process. Well, we are so proud of this company. TSMC right now, it's become a term just like a Coca-Cola. You don't have to explain it. Because Coca-Cola, you understand what that is, right? Okay, even that Coca-Cola is something like could kill. A lot of students don't like it. It's sweet, but it's a bad idea. Okay, do you know how, what is the name of that guy? The founder of Apple, Steve Jobs. Steve Jobs. Do you know how he died? Pancreas cancer. He drank 8 cans of Coca-Cola every day. 8. That's a lot of sugar. Okay, a 350 ml Coca-Cola, it has 8 spoons of tea. 8 spoons of sugars, sorry, 8 teaspoons of sugars. How much sugars you need every day? Only 1 spoon. And he drank averagely 8 cans of Coca-Cola every day. That means 64 teaspoons of sugar. And that's how he killed himself, with sugar. All right, Steve Jobs. Too bad. What a genius. Anyway, so we can say this is a slab. So basically, how we do the analysis is quite easy. Okay, there is no secret about that. So let's draw the figure here to see over here. Okay, let me draw the figure, even though I'm a very lousy artist. Okay, and this is the length. This is point A to B. Okay, and this is a height. This is the T. What is it? You use a T or what? Yes, T thickness. And this is W. This is W. So the definition of resistance, okay, the resistance is proportional to the length of the travel. And it is reverse or counter proportional to the area. And there is a constant in between the material. That's all. Okay? And this one can be equivalent to rho times L over A equal to W times T. Then because the T as a thickness, it is fully defined by the foundry. So basically the designer, like us, has no control about it. So usually we combine the rho with the T as this way. Over there, see, the same. Okay, it's the same. A very interesting result. So this is a constant, okay, given by the material. You can consider that for the metal, the rho is very small, so it has a very small resistance. For the polysilicon or diffusion, this one is big, okay, so it has a high resistance. So don't ever use that to carry the current, that's why. The interesting observation about this equation is that if L equal to W, that means it's a square. L equal to W. Then we have a fixed number of what? Of resistance. When L equal to W, then we have a square. And when it comes to the square, the resistance is a constant, because this is constant. And this is a constant defined by the foundry. We can do nothing about it, so this is a fixed number. So that is why we call a square, okay, the square. So L equal to W, then we're going to have a fixed number. It's called R square. So in the data sheet given by the foundries, UMC or TSMC, they'll give you a data sheet to tell you the square resistance of each material. Now let's go to the table, and you will find out. All right. So this is the typical. This is the process you use in this course. It's 180 nanometer, 0.18 UMC. Because this is a legacy process, these numbers are almost the same no matter which 180 you use. From TSMC, UMC, almost the same. So you have a layers of metal, 1, 2, 3, 4, 5, and the thickness is fixed. Okay, the thickness is fixed. And the height means that the bottom of the metal wire to the substrate is also a fixed number over here. Okay, and this is a width. This is the pitch, width and the space, minimum number. And then AR, this is something you should learn. It's called the aspect ratio. It is a thickness over W. Thickness over W. So it's about 2, somewhere around 2. All right, somewhere around 2. Okay, so there is no secret about it. Then we convert it into real numbers for you to understand. Okay, so we plug in all the numbers. Now, because the materials could be made by different metals, okay, silver, copper, gold, alumina, tungsten. Silver and gold are too expensive. We cannot afford it, all right? No one use that. Copper is too heavy. So copper, if you use the copper as a metal wire, because it's too heavy, it might sink to the bottom and kill the chip. So basically, unless you have a special process techniques, otherwise copper is taken out of consideration. So basically, all the materials, all the metal materials that we use in the school is aluminum. And this is the resistivity, micro ohm per centimeter. So, well, we don't have the best answer for that. Silver is the quickest one. That's why we call it quicksilver. Silver, copper, and gold, they are a very good candidate, but we cannot afford it, so we use alumina. And tungsten is too big, and that's why it's getting out of the market, okay? So we plug in all the numbers over there. For example, the 2.7, that's alumina, over the thickness over the top. So every square is about 56 milliohm for the metal 1. And for the metal 5, it's about, because it's bigger, okay, it's 17 over there. And then we can calculate if your metal wire is 0.5 centimeters, it's very long, okay, and width is 1, you can estimate before you go to the design, you know that the overall resistance is 280. So please do the calculation before you go to the computer and run the software. You got to understand what you are dealing with. Okay, I am not asking you to remember all of the numbers because I cannot remember it. I'm asking you to do the data check and do some estimation about how fast your circuit is. Okay, so this got to remember that alumina, the rho is 2.7. And as for the diffusion is a bad idea. Let me draw some figures, then we can stop right here to tell you why I don't ask my students to use the diffusion to use the diffusion as a resistor, because it's really not that good, because it's not uniform. So you remember that we talk about the diffusion. Diffusion is something buried under the substrate. This is diffusion. Okay, diffusion means I use a gas, okay, and then use a diffusion method. Even though you use the ion implementation, that's fine. The thing is, those gas atoms comes from the top, the air. So the concentration from top to the bottom, they are not uniform. So we have a very dense, dense particles on the top, and this is less dense. Okay, just like the one over there. This is concentration. This is surface 0, and this is the deepest part of that diffusion area. So as you can see, that blue curve tells you it's not uniform. It's not, for the metal wire, it's almost uniform, okay? It's only, but this one is not. So you have to do the conduct analysis like the one on the top over there, blah, 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 all the way down. And the bottom line is, not only the resistance is highly correlated to the L and the W, the size, the area of the diffusion, it is highly correlated to the concentration, and the concentration is the function of distance from the surface to the bottom over there. And these are mobilities and electrons, and you have to do the integration. Okay, you have to do integration. And this is the equation over here. So basically, and let me repeat again, it's not a uniform. You got to do a lot of mathematical analysis to find it out. And what even worse is that because it's not a uniform, so its accuracy is bad. All right, so let's check this out. I think this is the last slide. So no matter VLSI or VLSI you use, you check the numbers here. This is this column over here. This is R square. Every square, how big the resistance is. Okay, you see that N well, it's a 450 plus minus 100. What is the ratio of that? It's almost 1/4. The variation is about 1/4. That's large. For the diffusion, is 140 plus or minus 20. That's 1/7. It's our 15%. 15%. But if we check the polysilicon here, it's 450, 440 plus minus 10. That's about what? 2.5%. Which one is more accurate? Of course, polysilicon. So that's what I say. Don't ever use the diffusion or unwell to serve as accurate resistors on silicon. They are not. The variation accuracy could be 15% up to 30%. But for the polysilicon, it's about what? Here, 4%, maybe 2. So it's more accurate. Okay? So this is, please take my words for this one. All right? But for everything that, okay, these are numbers I gave over here. And before we go to the details of the next time, I'll let you know TC1, TC2, VC1 and VC2, that stands for coefficients, because the resistance of all the materials will be affected by 2 factors, temperature and the voltage drop on both ends. And these are their coefficients, the first order and the second order. You see, the second order is about 10,000 times less than the first order. So basically, this is to the minus 7, to this to minus 3. So basically, in our course, all I ask about the students is to take care of the first order coefficient, that's all. Second order, drop it. Okay, when you are a graduate student, you can do the research about that. All right? So the TR here. So we continue our talk in this coming Thursday. I will give you the next homework in the Thursday evening. All right? Okay, take a break, and you can go find your lunch.